PCAP's Native Prairie Speaker Series. My name is Caitlin Rose, and I am the Stewardship Coordinator with Saskatchewan Prairie Conservation Action Plan, or PCAP. Today, Julie Heinrichs, Research Scientist at the Natural Resource Ecology Laboratory at Colorado State University, will be talking about comparing the population benefits of habitat restoration options for Greater Sage-grouse in Alberta. Every month, PCAP asks someone to present either in the form of a webinar or an in-person talk in a Saskatchewan community on anything to do with native prairie conservation or species at risk. Check out the PCAP website for more information about our Native Prairie Speaker Series, as well as other events such as Native Prairie Appreciation Week going on June 17th to 23rd. I would like to take a moment to note that financial support for today's webinar is provided by Canada North Environmental Services, Environment and Climate Change Canada, Eco-Friendly Sask, Information Services Corporation, Rancher Stewardship Alliance Inc., SaskTel, and Wildlife Habitat Canada. In-kind support for today's webinar has been given by the Colorado State University. A reminder to all of our listeners out there, if you have any questions during the presentation, please feel free to type it into the webinar dashboard at any time, and questions will be answered at the end of the presentation. Julie is a research scientist with the Natural Resource Ecology Laboratory at Colorado State University, where she develops applied research projects in collaboration with the U.S. Geological Survey. She also conducts conservation and landscape ecology projects through Computational Ecology Group Canada. Her research uses spatial, quantitative, and mechanistic modeling to support conservation science and decisions. Julie's recent work focuses on long-term wildlife responses to source sink dynamics, management actions, and landscape change. Her current work emphasizes declining avian species across North America: Greater Sage-grouse, Gunnison Sage-grouse, black-cap vireos. She earned her PhD modeling Ord's kangaroo rats in Alberta. With that, I'd like to pass it over to you, Julie.
Thank you. I'm just starting my screen share here.
Everything looks good on our end, so I think you're good to go.
Okay. Okay. Thank you for the invitation to share some of the research I've been working on recently. I'm naive a little bit to who's in the audience, so please bear with me and ask questions if I kind of miss the mark. As mentioned, I am a research scientist at Colorado State University, but started this work just shortly after I finished my PhD at the University of Calgary, and I roped collaborators Cameron Aldridge, David Gummer from Parks Canada, Adrian Monroe at CSU, and Nathan Shoemaker from the US EPA and Oregon State University into this project to contribute to the various components. And we did this work with the support of Parks Canada and Environment Canada. So as most of you know, sage-grouse is a sagebrush obligate species, meaning they really depend on sagebrush for various aspects of their life history, for nesting, for cover, for raising their young, for food. They're also known for their elaborate lekking displays and congregations on these breeding leks, they call them. They're also considered to be an umbrella species because their habitat encompasses different kind of seasonal habitat needs for other species and other interests, in part because they require these largely intact landscapes for all their different seasonal life requirements. They're pretty broadly distributed, particularly historically. In light green there, we're showing the pre-settlement range, and in dark green, we're showing their contracted current range. So they have declined in their distribution in the past several decades as a result of different mechanism factors, chiefly habitat loss, degradation, fragmentation, and as a result of different kinds of threats. So range-wide, a lot of people are talking about fire, development and industry influences, land use change in general, different kinds of things, disturbance, climate change, disease. A number of factors are kind of combining to influence sage-grouse outcomes and where they are using habitat. Range contraction has also come with declines in abundance. Range-wide, it depends on where you look, what geographic extent you are querying, what management zone you're talking about. But generally, declines are observed in different parts of the range. And Canada, unfortunately, boasts the largest declines. So in Alberta, some are talking about a 98% estimated decline from 1968 to 2012, if you're counting total number of males at Lex. And similar declines are observed in Saskatchewan for 1988 to 2012. And unfortunately, the recent past is not too much different here below in the graphs. You'll see that the population size has declined from 2000 to 2015 and slightly increased at the end here, but majorly still on a declining trend for both the West and East populations. And just to pause here, the West population, what I'm referring here to is in Alberta plus the little bit of Saskatchewan that extends past the border, and East I'll refer to kind of the area around Grasslands National Park and associated sage-grouse habitat that is entirely within Saskatchewan. So as a result of all this kind of concern over range contraction and declines, there have been a number of conservation and management efforts. In Canada, as you're probably all aware of, the species has been listed under the Species at Risk Act as critically endangered, and associated critical habitat has been identified. Protection measures have been enacted, and there's a number of habitat management, conservation, restoration, and improvement projects that are ongoing, as well as less usual things like translocation and captive breeding programs. There's also some research and some projects on habitat prioritizations, and this is what I'll talk to you about today. In the US, it's a bit of a different story. They are warranted but precluded, so they're not a particular priority right now. And they've instead leaned on cooperative plans and actions and used kind of more of an emphasis on multi-jurisdiction plans and science-driven management to define what actions they'll take on the ground. So today I'll talk about the project path that I've been down, and that is to develop models to summarize and integrate Canadian sage-grouse habitat and population information. The aim was to evaluate sensitive demographic conditions to try to get at what the most rewarding aspects of demography to work on might be. Secondly, to spatially assess the opportunities for conservation actions, be able to identify on the map where better or worse places, more or less reward might be gained from conservation and management actions, and to compare how different restoration alternatives might impact population outcomes. So our approach was first to evaluate demography, second to construct a habitat population model, then assess demographic sensitivity within the context of that model, and use those constructs together to map habitat risk and sourcing dynamics, and then use the sourcing dynamics to look at habitat removal or restoration experiments to help us learn what might be the most effective approaches. So we started first by evaluating demography. So for survival, we looked at estimating Alberta chick, juvenile, yearling, and adult survival rates. We used input data from 1998 to 2006, leveraging and combining a few different data sets that were available that allowed actual estimation of demographic rates. And to do this, we used known Bayesian models. We didn't have a comparable data set for Saskatchewan, so unfortunately we restricted this analysis to Alberta. Same for nest success. We used a similar data set, similar years and sources from Alberta to look at nest attempts. So we combined first and second nest attempts for yearlings and adults. We also looked at the probability of renesting after failed first nest. And we did so using generalized linear models. So these were the results. We had chick survival measured from kind of hatch to 36 days. We also have DSRs, but for the purposes of the next step, we kind of chunked it into these different time intervals. So we have a mean and a standard deviation, which we use to construct normal distributions from which we could annually kind of sample and apply to the population each year to create demographic stochasticity among years. We also added those two values together to get this kind of elevated value that we used in sensitivity analyses, which I'll describe in a little bit. New to Canada is our estimation of juvenile and yearling survival rates from kind of a full-on estimation-based process. So we similarly created distributions for these other life stages and applied them in the habitat population model that I'll describe next. So this is primarily female data because male data was limited. And if you want kind of more details on the methods and some of the other results for different time periods, you can find it in the manuscript we recently released. So in terms of reproduction rates, we have nest survivorship. So for first and second nest combined for adults, separately from yearlings. We also have a renesting probability that we used to allow individuals to have a second chance, essentially, at producing a clutch in a given year. We combine these in the habitat population model, similarly to how we did that for the survival rates in terms of creating distributions from which nest survivorships were sampled every year. So we constructed a habitat population model. And although a lot of the models are created for habitat only or population only kind of processes, we wanted to embark on this modeling endeavor that combined them both because habitat and demography are intertwined, particularly for sage-grouse in Canada. Population sizes and their distributions and their demography are modifying habitat use, and kind of vice versa. The habitat, the conditions, its distribution, its abundance, its patterns end up modifying population sizes through demography and distribution. We're also finding that the details of the system really do matter. So particularly for sage-grouse that have these strong site fidelities to leks and nest sites, those fidelities seem to trump other kind of mechanisms that might dictate where they might select habitat. And there's a cascade of effects that kind of flow from that behavioral attribute that causes individuals to select habitat differently, survive there differently, and then ultimately reproduce differently and pass that behavior on to subsequent generations. And so the pattern of habitat quality also matters. We're finding that there are areas on the landscape from previous research that are both highly selected and highly risky. And there are areas that are, highly selected and not risky. And those areas can create sources and sinks and incite what we call source sink dynamics. And that complicates how you might manage and care for a landscape and species. So we wanted to really jointly evaluate all of these things together to get a more realistic picture of how local resources, risk, demography, movement, and behavior all combine to modify population outcomes and nuance how you might affect change on the landscape. So sourcing dynamics was of interest to us because it really describes the net demography and movement characteristics. So we have births and immigrations and deaths and emigrations that happen in these interconnected aspects of the landscape. Sage-grouse habitat doesn't tend to be incredibly discrete like this, but there are definitely areas that are stronger in terms of supporting sage-grouse needs and areas that are weaker and detrimental. And the interplay of individuals seeking out different places and moving among those different places has implications for how you might both conserve areas on the landscape and try to improve them. So we thought this might be a good way of kind of conceptualizing and testing how you might prioritize and chunk up the landscape to figure out what might be the best approach to making improvements. So the habitat population model we constructed requires a bunch of different inputs, or we decided that it required a bunch of different inputs. So we gave it the number of birds, so we used LEC counts. We also informed it with demographic rates, those ones that I showed you. We pulled survival and reproduction rates, turned them into distributions that we could query as the simulation progresses through time. We also fed it behavioral rules. So we looked at empirical data describing movement, habitat selection, and site fidelity, and programmed those into how the model works so that those factors are also considered. We explicitly included habitat in the form of resource selection maps and risk maps in Alberta, and maps of active LECs. So all these different types of data were present and interacting within a spatially explicit individual-based model. We then modified some of those inputs to create alternative scenarios so that we could look at how outputs might change through time by comparing abundance, probability of extinction, patterns of habitat use, and what will amount to sourcing dynamics, those locations and counts of births and deaths, immigration and emigration events. So we had to do this in a slightly different way for Alberta than we did for the rest of the Canadian range. In Alberta, the area I've labeled here, kind of west risk in orange, describes the spatial extent that we could apply season-specific habitat selection layers and risk layers describing where individuals would do better or worse during a specific season. Elsewhere, we didn't have that kind of information, so we relied upon a spatial model that kind of combined the influences of different habitat factors on habitat selection. And so we were really only able to do the sourcing prioritization for this orange area in Alberta. So population inputs more specifically included LEC counts from the years 2000 to 2016, those demographic rates that we talked about. In Alberta, those demographic rates were specific to that area. As I mentioned, in Saskatchewan, comparable data sets were not available. So we applied the Alberta survival and reproduction rates. And we used, obviously, the LEC counts from Saskatchewan for that population as well. In Alberta, we also looked at Alberta-based movement distances. So we used Cam Aldridge's LEC to nest data set to characterize the distance traveled between LECs to nest to establish a nest. We also borrowed a Wyoming distance from nest to brood rearing so that we could, in the simulation world, move individuals that had nested in a specific location, a specified distance or a range of distances to a brood rearing location so that we could supply it and reference that brood rearing map. We also included behavior such that individuals would remember the LEC that they attended and they would return there in future years. we did a similar thing for nest sites. And that was to kind of emulate the behaviors that we observed in the field systems. We did a similar thing for Saskatchewan, substituting some adjacent tax movement distances from his 2009 work. For habitat, we in Alberta used the selection maps generated by Aldridge et al. 2007. So that described nesting and brood rearing in two different maps, the probability of selecting specific areas based on their resources. We also paired that with demographic risk maps describing the probability of success in a given location for nests, as well as a different map describing the probability of chick survival relative to other areas in the landscape. In Saskatchewan, we didn't have this kind of season-specific or risk-specific spatial data, so we used that Canada-wide resource selection surface created by Parks Canada, Environment Canada, to move individuals through the landscape. But their success was not tied to locations on the landscape as it was in Alberta. So the mechanism to kind of tie this all together was this habitat population modeling framework that I developed within this program called HEXIM. HEXIM supports spatially explicit, individual-based and trait-based models that you essentially define yourself to capture the most important elements of a landscape, of a system, of a population, and the connections between them to represent the problem and the system that you're interested in. So individual-based, I mean, we're representing unique individuals that have unique traits, and their outcomes are modified by those traits, experiences, or their location in the landscape. We're tracking individuals through space and time, and through heterogeneous habitat. They know they can look at the maps, they can query the spatial pattern, the quality, and the selection values of the maps that they're referencing. So we built this with mechanisms and rules, with distributions, with stochasticity, as a way to try to create a simulation analog, a simplification of a complex system with the right kind of balance between realism and parsimony, trying not to be too complex, but representing the things that we think really matter for making decisions in this landscape. So each individual here is a line, and an arrow is describing their location. This isn't in Alberta. There's far too many arrows here. This is a Wyoming example, but we're tracking individuals through space and time, and their attributes are impacting where they choose to be and ultimately what their outcomes are. So getting into the weeds a little bit here, annually, this is kind of this cycle of events that we're walking Alberta birds through. So we're starting them at their 2000 lek distribution and abundance. We allow them to move from their preferred lek to their nest, and then they establish a nest there. In Alberta, they're referencing that nesting specific map. They remember their nest site. They take an attempt at a first nest. Whether they're successful or not depends on where they are in the landscape, what success rate is pulled from that distribution that year. If they're unsuccessful, a certain proportion of them are allowed to re-nest according to the empirical data. They're allowed another second nesting attempt if they're assigned that attribute. And then they move to a brood rearing habitat, referencing that brood rearing habitat selection map. They survive according to their location, the chicks, and the distribution value pulled. We deal with annual survival of all life stages, aging, and at various points we're recording where they are in space and relative to other individuals and habitat features. They are returning to a familiar lek or setting setting a rule to remember a lek that they were at recently. And then they repeat the cycle each year. So that gives us the basis of trying to represent a system without actually experimenting with a large, vast landscape and complicated system that we couldn't hope to do in a realistic manner. In terms of alternative scenarios, we looked at not only those baseline rates, but those elevated mean plus standard deviation values to try to get at how much change might be required to stabilize the population or perhaps increase it. We also looked at what kind of variables you might change that might give you the most kind of return on your investment. So we standardized the changes according to how much we changed the input variable. We also looked at what to do about the landscape. We have these sinks. We have individuals in them that may not be doing so well. Would removing them be better than restoring them? Would we target weak sinks over strong sinks, or would we do the opposite? What might be the best tack in this complicated system? So in terms of results, what we see is that the baseline predictions do a pretty reasonable job of emulating this gray line, which is the kind of extrapolated lek counts to account for individuals that aren't attending leks. So the baseline is this blue line with a square, and so we see that it's a pretty close replication in the first few years, and then when we get back to like shortly after 2010, it does a good job. There's a period in the middle that is less in line with the straight demographic kind of predictions, and there's a slight upturn at the end that is also a deviation from those predictions as well. So there's a few things that could be going on here. One is that the demographic data was likely collected in years that were a little bit more pessimistic for various reasons, a little bit more harsh than we may see in subsequent years. There are things like West Nile virus outbreaks, more oil and gas activity, population cycles and weather cycles that happen that kind of cause deviations from what you might expect from a very average linear kind of extrapolation. So each of these lines represents a mean population trajectory averaged over like 100 simulation replicates. In terms of extinction risk, you see that the risk of falling to a population size of 0 is pretty substantive, particularly as we approach modern day times. And if you look at the different scenarios here at the bottom, here we're increasing demographic rates as we did in the previous slide to various levels. So we're heightening reproduction to that mean plus standard deviation value and survival to that mean plus standard deviation. And in all demography high, we're combining all those high estimates together in one scenario. And under that version, we see a much reduced risk of extinction. However, it's still pretty high at 0.6 approximately for the west and east populations. So these two both kind of suggest that a pretty large push, pretty large increase in demographic conditions is likely to be required to start to stabilize and increase the population. Looking now at growth rates, we see the baseline growth rate is anticipated to be about 0.6. Looking across the different sensitivity scenarios where we've increased demography, we see improvements, but none of them really get to the mark of 1, which really signifies a stable population. If we look instead at the change in lambda per unit, change the standardized measure of how much kind of change you'd see per unit effort, we can look and see that adult survival nest reinitiation, and chick survival seem to be the top kind of 3 variables, the most responsive parameters to increasing growth rates per unit change, per unit increase in that demographic condition. In the east, with a different population size, different kind of habitat and model layout, we see slightly different results. We see a real emphasis on the responsiveness of chick survival, also adult survival, and to a lesser extent, other variables. So those kind of outcomes emphasize that there seems to be some clear winners in terms of life stages that you might target for improvements. The survival of adults and chicks, and perhaps nest success or nest reinitiation might be good things to kind of key in on and try to figure out what you can do to help those conditions. So in terms of the future trajectory, overall long-term, I think you'd average it out and call it a decline. But in the last few years, Alberta and Saskatchewan population sizes kind of slightly increased. You saw that upturn at the end. This could be a result of conservation actions, protection, climate and population cycles, stochastic events. It's pretty tough to kind of pin that result on any specific kind of thing. But what is clear is that those short-term improvements need to happen for a long amount of time, and need a strong push to really elevate the populations, to reverse those declines, to stabilize them, to increase them, to improve demographic conditions, to achieve stability. And these results, I think, show that actions can be somewhat strategic, and they can be targeted at specific life stages. So the second part of this project was to look at how much of those actions can also be targeted spatially. So we're looking here again at sourcing dynamics. And the funny thing about sage-grouse and a lot of other species too is that site fidelity or some sort of choice is overriding selection of higher quality habitat. So when we have lek site fidelity, returning to a familiar lek often constrains what area sage-grouse are nesting in. They often just search a certain kind of periphery around a lek site and then are constraining themselves to select a nest area within that. Nest sites, a similar idea, females often return to the same area even if their nest is unsuccessful in that location. So this complicating factor, I think, makes it necessary to think of the system in a kind of dynamic and interconnected kind of way, which makes it a nice fit for the source sync concept to come in. So sources are great, easy targets for conserving habitat. The habitat is usually pretty good there. The populations are doing well there. But the question again is what to do about the sinks. Is there a high restoration value there? What can you do? And to try to help figure this out, we conducted a source sync analysis using the Alberta portion of the model. So here you're seeing a graphic that is full of hexagons. And each hexagon contains many other little hexagons. And what we've done here is summed up all of the births and immigrations and deaths and emigrations within those individual hexagons, and then kind of generalized those into these larger hexagon shapes. So we've done that over the entire simulation period and just made this kind of global spatial characterization of what sources and sinks would be. Here, we're seeing sinks in red and sources in blue, giving us kind of this first pass at where you might characterize good places for sage-grouse and not so good places for sage-grouse. But what do you do about sinks? Are they good to have around? What is their impact on the population? Can you restore them? So we conducted all of these different alternative scenarios to try to get at that question. So firstly, we removed all the sinks, so all these what I'll call BIDE metrics that resulted in those below zero values. So that was the kind of red to yellow spectrum of that map, and replaced them with non-habitat niche seasonal map. We did this with only the kind of stronger things, so that kind of middle area of the hot spectrum, and only with the very strongest things, the very red hot by minus 500 values and below. We compared those outcomes to what you might see if you restored sink habitat. So we looked at all sinks and restored the chick survival conditions. So we looked at that chick survival map and did habitat improvements to increase survival conditions within that map. And then compared that result to if you only did that for those very strong sinks. And what we found was that restoring sink habitat was a lot more effective than simply removing habitat. So if you looked at the number of individuals gained in the population 5 years after you conducted this habitat restoration action, we found that there was, looks to be 3 to 4 times more individuals in the population if you restored habitat versus removed it. And that's not surprising because you're retaining habitat, you're improving the quality, more individuals could presumably use the same area. So what you can't necessarily see in this graph is that the conservation outcomes are roughly equivalent, but substantially different in a way from these two restoring options. So in one, we're restoring chick survival conditions in all sinks, which implicates a huge amount of area within the landscape. And we're getting conservation outcomes that are similar to this other scenario, restoring chick survival conditions in strong sinks, which implicates a much smaller proportion of the landscape. So even though we're getting equivalent outcomes, the effort required to achieve that outcome is much, much less if we're targeting just those strong sinks. So that suggests to me that that targeting habitat restoration actions to specific sites is likely to increase the effectiveness of the action, not only by improving your outcomes, but by saving a lot of time, effort, and resources. And that restoring these strong sinks is probably the best strategy to return to conservation kind of investment. So for strong sinks, some of the recommendations might be that one, to prioritize avoiding further degradation of sources and having the creation of sinks. Secondly, to focus on restoring sinks to source conditions. And we experimented with chick survival as the means by which to do so. But one could also focus on other life stages that seem to be responsive: adult survival, nest success, nesting habitat in general. So our analysis stopped at the point of that in terms of evaluating just these general ideas of is spatial targeting rewarding? How might you do that targeting spatially? How much you do it to address different life stages? What we didn't do is go back and data mine our results to say what are the exact factors that we think are associated with restoration success and sinks and so forth. But we do have some of the input data that we can go back and look at to indicate what some of the effective kind of variables that one could manipulate. And so this range-wide kind of multi-season occurrence model from Parks Canada, Environment Canada include variables like moderate shrub cover, patchy distribution of shrub cover and sage, limited bare ground, moist vegetation, limited human use, noise, artificial structures is also supported by other research. So some of those things are kind of just generally things that you can manipulated, as I'm sure you all know, to improve habitat and quality for sage-grouse. Digging more into kind of the details in Alberta, we see similar kind of things in terms of where individuals select to be, with sage and patchy vegetation structure and cover being important, and avoiding some areas that are associated with edges and human influence. And there are some variables to do with survival and risk that can be kind of leveraged to try to create some change. So here, nest survival was associated with vegetation greenness, so the things that you can do to improve the presence of a reasonable amount of moist vegetation. There are lots of projects going on in the US to kind of create nice mesic habitats and so forth that might be able to make a difference for nest survival. Planting and managing vegetation structure seems to be something else that people are focusing on as well. In terms of brood occurrence, there's lots of things going on here that one could investigate in terms of development and trails and being closer and having access to water and croplands and urban density and different kinds of habitat characteristics that encourage birds to be in certain locations and not in others. Be helpful in a location in terms of context. For example, you might cite a conservation action somewhere where the context is favorable versus not favorable. You can't change a compound topography index value that chicks seem to be responding to in terms of survival. But you can change things like choosing not to have a conservation action or an improvement in an area that has unfavorable CTI values versus favorable CTI. Demonstrates that while there is improvement, there is still a need for these multiple simultaneous actions to stabilize and recover the population, and that there's a lot of kind of long-term actions that probably need to happen in the future to achieve population stability and ultimately persistence. The small piece of the pie that we bit off in this project suggests that targeting restoration of strong sinks and addressing habitat and population threats that look at things like adult chick survival, nest success might be helpful in getting a little ways down that road. Helping in the future also would be addressing some of the data gaps. There are a lot of things unknown about the Canadian population and habitat. Some of the things that we noticed when we were doing this project is that we lack some recent habitat data and responses to habitat in terms of what individuals are choosing to select. Some of the data that we have used has been the best available, but is somewhat dated. It would be great to have more complete information regarding habitat range-wide and multi-season habitat maps range-wide, including summer and winter. We don't know too much about male-specific demography and habitat use. We seem to have a lot more information for Alberta than we do Saskatchewan. And so having a better representation of what's happening in Saskatchewan in terms of habitats, environmental conditions, habitat selection, and demographic rates that we can kind of use to estimate similarly to how we did it in Alberta would be, I think, helpful in trying to figure out and predict the trajectory of that population a little bit better. So that kind of wraps up that project, but a lot of that modeling is now kind of rolled into the next effort that I'm working on with the Calgary Zoo, which is looking at egg collection, captive breeding, and release. And so the gist of this project is really just leveraging and borrowing a lot of the information that we developed for the project that was looking at sourcing dynamics and population trajectories, and trying to figure out how collecting eggs from the wild might impact source populations, how you might grow a captive population and produce a surplus for release into wild populations, and how releasing birds into the wild populations might result in positive growth for wild populations. If you're interested in hearing more about any of the other kind of projects I'm working on, I'll just kind of give you a very quick overview of some of the things that are going on in the US that I'm involved with, and I hope that you'll reach out with an email or phone call or something like that if you want to chat more about them. First is this project looking at post-fire restoration of sagebrush and sage-grouse populations. So at the USGS and CSU, we are planting sagebrush and growing it in an area affected by fire. We are simulating regrowth and vegetation transitions to try to predict how long that might take to see the ecosystem kind of restored and the sagebrush functioning and the populations returning to those areas. And ultimately trying to evaluate the scope of recovery action required to get the system back to where it was pre-fire. Also working with USGS and BLM to assess the ability of fuel breaks to change fire behavior, simulate sage-grouse responses to fuel breaks, fires, and habitat loss, and how adding these things onto the landscape, these massive fuel breaks and infrastructure, might affect the proliferation of fine fuels such as cheatgrass. I'm also finishing up work on predicting kind of the range of impacts of development and climate on sage-grouse populations. So this project involved essentially using some modeling and some build-out development plans to try to map out the spatial footprint of future energy activities, as well as climate-induced vegetation changes, how that might influence habitat selection for sage-grouse, how the addition of indirect impacts such as avoidance of energy structures might affect future distribution and abundance, and ultimately kind of simulate the range of possible outcomes of sage-grouse abundance and distributions to those combined effects. We are also modeling venison sage-grouse habitat selection with a focus on developing conservation planning and prioritization tools to cite conservation actions, reduce threats, and improve population outcomes. And with that, I'd like to kind of thank you for your patience and listening to me stumble through my words today. If there's anything that I didn't cover here that you want to know the details of it, you can find some more info in our recent publication in Biological Conservation. And I would also like to thank Troy Willicombe, Ryan Fisher, Mike O'Donnell, Kira Monroe, and everyone else who contributed to this effort. And thank you very much.
Thank you, Julie. That was a really interesting presentation. It looks like you've done a lot of work for sage-grouse. To all of our listeners out there, if you have any questions, please feel free to type into the question section of the webinar dashboard. And I would just like to remind everyone that when you leave this presentation, there'll be a quick questionnaire that'll pop up. If you don't mind filling that out, just take a minute, and that'll allow PCAP to continue on with webinars into the future. You're also welcome to check out the PCAP website, www.pcap-sk.org, and click on Communications and Native Prairie Speaker Series. This webinar has been recorded and will be uploaded to YouTube later today, and you're welcome to share that with some of your relatives who are not able to make it. Friends or relatives or colleagues who are not able to catch the presentation today. If there's any questions out there, please feel free to type that in. We do have one question at the moment. Julie, could you just tell us a little bit about how you got into sage-grouse work from the beginning?
Well, I was just working at the University of Calgary, and actually David Gummer from Parks Canada was on my PhD advisory committee from Orr's kangaroo rat work and asked me to kind of contribute to this effort that he was starting to build upon some mapping that he had done for sage-grouse in Canada, and then it just kind of spun out of control from there. During that project, I met Cam Aldridge, who was working at Colorado State University, and he ultimately convinced me to leave the University of Washington, where I was doing my postdoc on sourcing dynamics, to join the U.S. Geological Survey and their large campaign to do a lot of sage-grouse work. So I've been there ever since, and it's been an interesting journey.
Great, thank you. One of our listeners would like to know, what do you think is going to happen with the sage-grouse population in Canada? What do you think are our best steps to protect this rare species?
That's a tough one. I think it's hard not to see the very small numbers of individuals in both Alberta and Saskatchewan and not feel concerned for their trajectory. I feel like the recent upturn is cause for some hope that perhaps the actions that we're taking are being helpful. But I think it's far too early to declare any sort of victory without long-term kind of dedication to making sure that there are strong habitat and population kind of actions and interventions that are going to result in continued stability and increases. I don't think there's any, specific silver bullet of sorts that is going to fix the situation. I think it has to be multiple different actions happening at the same time with a lot of thought and planning and cooperation that is going to make the difference. I think it's got to be proactive, and it has to be ongoing.
Good, thank you. That's a great answer. One of our listeners would like to know a little bit more about the Gunnison sage-grouse and what can we learn from that species that we can apply to greater sage-grouse. So one thought is that Gunnison sage-grouse has got this very large kind of central population that has, a few thousand birds in it, but it's got these little satellite populations that have really been not the focus of a lot of conservation efforts. They've gotten to be very small, not terribly unlike what we have in Canada, and they've gotten to the point where they are too small to start experimenting on. They're too small for a lot of actions, a lot of research, and I think we have to make sure that our populations don't fall by the wayside and get neglected, and that we are, addressing every population, no matter what size it is. That's a great answer. Thank you very much for that. Another listener would like to know, how can an individual get involved to be part of the conservation efforts for sage-grouse?
Also a good question, and I wish I had the answer. I think I'm probably the wrong person to ask, because I have my notes in the computer and the books a little too much and a little too little on the ground and in the action in terms of doing things that result in people contributing to actions. But I think there are a number of groups in Alberta and Saskatchewan that are interested in getting people involved, and certainly there are a number of organizations in the states that they're actively pursuing, public participation in various projects. But I'm not familiar enough about what those groups are doing in Alberta to make a recommendation.
Thank you for that answer. For a listener out there who did ask that question, I believe Grasslands National Park has a sage plug restoration program where they're putting sage plugs out in the ground, and they're also marking fence lines. So you can look that up at Grasslands National Park. But I know there's a number of other opportunities out there for a person to be involved with sage-grouse conservation. That looks like all the questions that we have at the moment. I would just like to take a minute to thank our webinar sponsors, so the groups that have made our Native Prairie Speaker Series possible. That's CanNorth, Eco-Friendly Sask, Environment and Climate Change Canada, SaskTel, Wildlife Habitat Canada, Information Services Corporation, and Rancher Stewardship Alliance, Inc. It looks like that's all the questions that we have today. So with that, I'd like to thank you very, very much, Julie, for the really informative presentation. It's so timely because the sage-grouse numbers are so low. So we really appreciate all the work that you've done and that you've taken time out of your day to share that with us. So thank you, Julie.
Well, thanks so much for the opportunity. I appreciate it.
And thank you to all of our listeners out there for tuning in. So with that, have a great day, everyone, and hopefully you're enjoying this beautiful spring weather. Thank you, and bye.